All right, so our goal here is to develop an equation where you plug in some initial concentration and a time, and you get the concentration at that time. Now, this is a little more complicated than it sounds because, as we've talked about before, the rate is continually changing because the rate depends on the concentration. And it's actually not quite as bad of a problem as you might think it is because of calculus. I'm going to go through this derivation for you. Now, if you are not in calculus, I will tell you what the answer you need to know is. If you are, take a look, because this is one of the most simple and elegant applications of integral calculus. So the idea is that, let's start from our original rate equations, right? So we've got, A is decomposing into 2B plus C or something like that. And we're going to talk about the concentration of A. So we're going to call the rate of this concentration, and I am going to, because of my bad calculus habits, I've gone away from the delta and using this little d function here, which just implies that it is a really, really, really small change, or infinitesimally small, as the mathematicians call it. So the rate of this reaction is going to be equal to the quantity dA dt. So this is just the change in concentration of A with respect to the change in time. And since this is first order, this is equal to some rate constant K times the concentration of A to the first power. Now, the way that we get rid of these infinitesimal or differential operators is by integration, and that's why these are called integrated. This is why what you're about to see in the end is called an integrated rate law. So what I do is isolate the different variables, in this case the concentration of A and the time, on different sides of the equation. So I could say that the quantity dA over A is equal to negative K dt. Now the negative K could have gone on either side, just the convention is that you kind of move it over away from the concentration and keep it with the time component. The end result would be the same. So the way that you get rid of these infinitesimals is you integrate both sides of the equations. So here I've got the integral of dA over A being equal to the integral of dt, and I'm going to put the negative k out in front because you can do that with constants and integration, and it makes life a little bit easier. Now the last thing to consider is what the bounds of these integrals are, and I will just tell you. The bound of this integral is the initial concentration A0 and the final concentration A at some period t. The bounds of this are the time bounds, which are 0 and then time t. And then let's start a new column here. Just integrate. So the integral of 1 over x, you might know is just the natural log of x. So here I've got the natural log of A evaluated at the bounds A0 and A of t, and that is equal to, now you don't often see this in calc, but the integral of dx is just x. So this is just negative k times, I'll just put this in a parentheses here, and here you've got times time evaluated at 0 and time t. And this bar notation, if you haven't seen that, just means evaluated at the upper limit evaluate it at the lower limit, and then take the difference. So this is going to be the natural log of a at time t minus the natural log of a at time 0 equals negative k times t minus negative k times 0, and then so that we just drop out because it's 0. And here you've got, so just to clean that up, natural log of a at time t minus natural log of concentration of a at time 0 equals negative kt. And to clean this up often, we just say the natural log of a at time t is equal to, actually, whoops, apologies, forgot a negative sign here, is equal to the natural log of the concentration at time 0, the initial concentration, minus the product of kt. And now I want you to remember this form, because this is one of the ways that this is often reported. But I want to take things just a little bit further. And so one way you could do is you could get rid of these natural logarithm terms if you were so inclined. First, you would isolate them together. So what you could say is the natural log of the concentration at time t and the concentration at time 0 is equal to, see, this product of negative kt. And the way that you get rid of the natural logs is you do an exponentiation operation. So that would mean, okay, I need too many more lines here. That's the ratio a at time t over a at time 0 is equal to e to the minus kt. Or the way that this is normally seen is with one little rearrangement. A at time t equals the concentration at time 0, e to the minus kt. And this is the other way that we commonly see this. Now, as I said before, both of these are called integrated rate laws. I'll write this down here. And they are named such because you get to that answer from integration. Now know that both of these guys, this one and this one, are the same thing. So use either one you like. Typically, if you are just looking for concentration, you know, our initial goal right here, just to find this. This is the one that you want to use. There's another reason why this one, the natural log version, is more convenient. So let's talk about that. So let's look at what this would look like graphically. All right, so we're going to plot, just want to start plotting the concentration as a function of the time. And what the equation that we just derived implies that it's going to be an exponential decay. Now, exponential functions are, or at least back in the old days, were fairly tedious to analyze, which is why in some cases you will see the natural log version of the equation, and here's why. This is because the natural log version of the equation is actually linear. And this was, back in the old days, kind of an important thing because linear equations did not require high-powered computers to be analyzed. They required a ruler, or if you were in a pinch, a book with still an intact hard edge. So here's the exponential version of the equation that we played with before. And let's go back to the natural log version. So the natural log of concentration of A as a function of time is equal to the natural log of the concentration of A0 minus KT. And this, it doesn't maybe look like it at first bat, but it is in fact a linear equation. So you've got, your y, and that's going to be equal to the intercept B plus the product of the slope and the x value mx. And when you write it like this, I would like to think that it becomes fairly clear, what's what here. So this maps to y. Your intercept is going to be the natural log of the concentration at time 0. Time is your x variable, which means that the slope ends up being negative k. So let's see what that would look like for, a run of several, natural log temperatures. So that is that you would plot the natural log of the concentration versus time. So this is, this is the y-axis and this is the x-axis. And now that same data is linear. And the slope of this line is equal to the opposite of k. So the linear version is actually much more useful to determine the rate constant. In my opinion, the exponential version is much more convenient to determine a concentration at a particular time. And as I said before, the intercept is equal to the natural log of A0. So interestingly enough, you don't actually need to know what the true initial concentration of a reaction is. And quite frankly, that is a difficult thing to get at because if the reaction is really fast, you might not have time to actually measure the real initial concentration. But in this way, you can extrapolate to it. And this actually is the preferred way of determining the rate constant. So a few lessons back, we talked about the isolation method, and you could sort of solve for the rate constant. This is actually, because it relies on many different measurements, the preferred way of determining the rate constant for a first-order equation.